I'd like to thanks to organizers for invitation, and I warmly welcome professors from Fudan University to visit Kaist. Yeah, cohomological invariance is an invariant of principal homogeneous spaces taking values in Galois cohomology groups. So let me give a formal definition of cohomological invariance. So we consider algebraic group G over a field. Base field F, and we consider the first Galois cohomology set for any field extension K over F, the separable closure of K over K, and the separable point of G.
KF?
Yeah, K is a field extension over F. And we simply write this as H1 of K G. And when one has a Galois module, so we have a commutative group and over F, and we simply write HD of K or HD of K C for any Galois cohomology group. And degree D cohomological invariance is a natural transformation from covariant functor from this G torosaurs or first Galois cohomology set to our cohomology with Galois module C, so that we have following commutative diagram. Or field extension R over K over F. So the basic idea is to understand this principal homogeneous spaces, the set, by attaching group cohomology to this set. And indeed, the notion of cohomological invariance was introduced by Searle 90s, and it's also introduced in his famous book Galois cohomology. And if we put together all the cohomology invariance, then it becomes a group. And this group is denoted by invariance of degree d of G, proof of or cohomological invariance. And we have a obvious invariance. This is an element of HD of F, the base field. So any element G torsors goes to an element of HD of F. So it's called constant invariance. And then we can normalize the group of invariance in this way. So and the invariance in degree d such that alpha maps every trivial cocycle or trivial torsors to 0, or distinguished elements goes to 0. So, in other words, any cohomological invariant of degree d can be written as some constant invariance plus some normalized invariance. And we will write this subgroup as invariance of degree d normalized invariance. Okay, let me give some well-known examples. So we consider orthogonal group of rank n and the coefficient to be just sigma to z. Then any element in our principal homogeneous space or G torsors can be identified with a non-degenerate quadratic form of rank n. So we can rewrite this as some diagonal forms. This is a notation for diagonal forms of quadratic form. Non-zero elements in K. And for non-degenerate quadratic form, there are many well-known invariants. First of all, we know the dimension of quadratic form and modulo 2, and this is in degree 0 invariance, which is isomorphic to sigma to z. So here the Galois group acts on C trivially, and we also have discriminant of quadratic form, which is just square class of multiplication of these AIs. This is in H1 of K. This is square. And for degree 2, we have a Hasse with invariant, Okay. The sum of quaternion algebras generated by AIJs, which is in degree 2 cohomology, and this can be identified with two-Torsion-Brauer group. Okay. And this is Hasse with invariant. And yeah, in general, we have a Whitney-Stiefel class of quadratic form. This is given by the coproduct of AIs. The symmetric functions. And this is Stiefel invariant. And yeah, moreover, one can show that the graded group of invariants of orthogonal group is a free HF module with basis the Whitney-Stiefel class. So in this case, these cohomological invariants are used to describe the already known invariants. And when G is a symmetric group, and again we take a simple coefficient, then one can also use this Whitney-Stiefel class to give a homological invariance of symmetric group in this way. So you just compose the G torsor, Sn torsor is some étal algebra, and F is a polynomial of separable polynomial of degree n, and we just let this be A, then the trace of this étal algebra is a quadratic form, and this is defined to be the usual trace of left multiplication. And then you compose this with Whitney-Stiefel class. Then this gives an cohomological invariance of symmetric group. And in this case, the cohomological invariance vanishes if m is bigger than or equal to the integer part of n over 2. So alpha exists only for m between 1 and integer part of n. So once we know some invariance for given torsors, then we can describe it by using already known invariance. But if we don't know any invariance, then in general it's hard to find or compute cohomological invariance. And so we consider the invariance, group of invariance, degree-wise. And for the degree 1 cohomological invariance of and its normalized part is known to be trivial if G is connected. And when G is a semi-simple group, and we consider the group of all nth root of unity, the mu n, then we consider the universal covering of G and with a central group, subgroup. Then from this exact sequence, one has H1 which is just Brauer group of K. So here, this is the connecting morphism from G to M. And this map is induced by the character. So here, the chi is in the character group of our central group. And so and this invariant is denoted by alpha sub k. So the character group of our central group maps to the degree 2 invariance, though normalized. And it is known that this is an isomorphism. So,
do you suppose that the universal covering exists in this case?
For semi-simple group, split semi-simple group, we have a simply connected cover. So we know degree 2 invariance for semi-simple groups. And so Now we move to degree 3 invariance. Okay, and so again, G is semi-simple. And now we consider the coefficient C to be the tensor product of nth root of unity. Yeah, and then you have this central subgroup and a base field, and we know this is degree 2 invariance of G. And then we have a canonical pairing from this group to degree 3 invariance, the normalized invariance. By taking coproduct, so we have alpha chi and some element A in F, and this image of this invariance is given by C and coproduct of A. So this is in page 3. Okay. And the image of rho is denoted by decomposable invariance of G. And so this is a subgroup of normalized invariance of degree 3. And yeah, indeed, if F, our base field, is algebraically closed, or G is simply connected, then this decomposable group vanishes. That is because the degree 2 invariance, this normalized invariance, is in general isomorphic to Picard group of group G, and for simply connected group, Picard group is trivial. And for algebraically closed field, so this decomposable group is trivial because let's say this image to be A, because this is in Brauer group, so this can be represented by some simple algebra, and coproduct of A is 0 if and only if A is in norm reduce of this algebra. And since F is an algebraically closed field, so one can find such B. So if you assume base field is algebraically closed, then there is no decomposable invariance. Okay. And in general, it's known how to compute the degree 3 invariance. So T, let me say T is a split maximal torus. Group G, and let's say G is simple group at this moment. Simple G, and then it's known that the symmetric square of the character group of split torus is the just infinite cyclic group. Generated by a quadratic form phi. I'm sorry. This W invariant of this symmetric square, and W is a Weyl group. Yeah. So, for instance, G is a special linear group, and then our torus is this, and this corresponds to character group. So we have such isomorphism, and so in this case, the phi, the quadratic form, is given by 1/2 of Ti square, but indeed this is an integral quadratic form. So and we know how to compute the indecomposable group, which is the vector group of normalized invariance by decomposable invariance. And this is just definition of indecomposable invariance. And this is a theorem by Rost and Merkuriev, and it's symmetric square and vector by some subgroup of this form. The generator is this form, and TIs from W orbit, and all indecomposable invariants are computed for semi-simple groups. But even though we know all indecomposable invariants, sometimes we cannot recover the normalized invariance because the exact sequence splits, then we can find this normalized invariance, but in general we don't know such sequence, obvious sequence splits. So, okay. Let me give some examples. So, G is ln. So, adjoint group, projective general linear group, and simply connected group, and the group between simply connected and adjoint. Let's say some power of prime and up, and let me restrict it to the case of p is odd. Okay, then indecomposable invariance, and so for simply connected group SLN, the torsor is trivial, so there is no non-trivial invariance. For PGLN, one can compute this factor group. Then this numerator is indeed generated by some multiple of this quadratic form. And this is also a multiple of this quadratic form, and indeed they are same. So there is no indecomposable invariance. So for PGLN, we only have a decomposable invariance, which is the tensor product of character group of M, which is sigma then Z in this case, times this F, so which is and this. So for algebraically closed field, we don't have degree 3 invariance for this adjoint group of type AN. But for this group, we have indecomposable group is C mod PZ times our quadratic form phi. So this is C mod PZ cyclic group, and normalized invariance is just direct sum of this and decomposable invariance, which is in this case, and for p equal 3. And in general, we don't know such sequence split but for p equal 3, we know split, so we can recover the normalized invariance out of decomposable and indecomposable invariance. Okay. And there is an interesting cohomological invariance between decomposable and indecomposable, which is called semi-decomposable. So now we consider a special orthogonal group. And for this group, any element G torsor can be identified with a quadratic form of rank n whose discriminant is trivial. So we can rewrite this as in this diagonal form, and we map it to H3 to A product with the quaternion algebra, the class of quaternion algebra in Brauer group, generated by B and C. And of course, one need to show this invariance is well defined, which means once we have other quadratic form, which is isomorphic to this form, then the image should be same. But it can be shown. So let me say this invariant is alpha. Then this invariant looks like decomposable invariance because this is a degree 2 invariance and coproduct with some element here. But this is not decomposable invariance because this is not trivial over FR and adjoining variables, independent variables, ABC. So for the decomposable invariance, this degree 1 constant comes from the base field. But here, ABCs are in K, right? So you can take algebraic closure and you're adjoining these independent variables. Then over this field, this invariance is not trivial. So it's not decomposable invariance. So it's something between decomposable and normalized invariance. So let me define semi-decomposable invariance. So the reductive group over F and alpha is called semi-decomposable. If for any field extension and for any G-torsor, there exists some degree 2 invariance and some element in K such that the image of Z is just some finite sum of its degree 2 invariance and Xi's. So in other words, semi-decomposable invariance can be viewed as a locally decomposable invariance. And it does not vanish over algebraically closed field. And this example is due to cell, and so we can say that decomposable invariance is a subgroup of semi-decomposable. So this is the group of all semi-decomposable. It's a subgroup of normalized invariance. And in general, if G is semi-simple, G is simple, then it's known that any semi-decomposable invariance is decomposable if G is simple group. So this is due to Mercury F, Neshtov, and now Janeway. And this example, SO4 is a semi-simple group. And in their paper, they said that this is this example is mentioned, and so far this is all known semi-simple invariants. So one may ask the following question: they're semi-decomposable invariants other than SO4. So this can be this is isomorphic to this semi-simple group, SL2 square, and central group mu is the maximal central group, mu2 square, and their product is trivial. And recently we try to generalize this group, and we have the following result. So n equal 2, and let's say G is this product of GL2 n times, and by a central subgroup. And we also consider its derived subgroup, the semi-simple part, and by mu, and mu is a maximal central subgroup with this one relation. And then we compute the indecomposable invariance first. And this is sigma to z if n is bigger than or equal to 3, and this is trivial if n equal to and we also computed the indecomposable invariance of this semi-simple part, and this is always sigma to z for n bigger than or equal to 2, and indeed this n equal to 2 is the example SO4. And we also compute the factor group of semi-decomposable invariance over decomposable invariance, and this is also sigma to z only for n equal 3 and 4, and for the other n is trivial. The factor group of H is also n equal 2, 3, 4. So in other words, for any n, the semi-decomposable invariance exists only for n equal 3 and 4. And for semi-simple group, it's 2, 3, 4. These are all semi-decomposable invariants. So we know semi-decomposable invariants exist only for semi-simple group, possibly, but not every semi-simple group has a semi-decomposable invariance. And one can also describe such invariance, but I will skip that part. And instead of that, let me say something about proof. And for proof, we use the following exact sequence due to Merkuriev, Neshitov, and J. Nolin. So here H is any semi-simple group, and one has the following exact sequence. Can extend this sequence to the reductive group. And in general, for reductive group, this is not this map is not surjective in general, and this is codimension 2 cycles of certain generic variety, and it's a torsion subgroup. And let me explain this generic variety. This is a generic variety, and the construction is follows. So you choose a representation V of H such that there exists an open subset, and on open subset H acts freely, so stabilizer is trivial. And we also require that the codimension of this open subset is at least 2, but we can also make it satisfy this condition, because instead of V, you can take V times V, and so. And then we have a G torsor, H torsor, mod H. And then you take the generic fiber of the function field of U mod H, and let me say this fiber to be U bar, and then our generic variety is just this flag variety U mod B. And here B is a Borel subgroup. After you fix a split torus, and so this exact sequence holds for any semi-simple group H and reductive group G. So in our case, the X bar is indeed the product of n conics. AI, BIs are some generic elements, so you can think of AI and BI as variables. So, they are generators of quaternion algebras. And you can compute the torsion subgroup of this variety, and it's always Zima to see if n is bigger than or equal to 5, and it's trivial otherwise. So one knows how to compute this indecomposable part, and if you compute this torsion subgroup, then we can find this part as in the theorem. And indeed, this exact sequence comes from modification of exact sequence from proved by Collier-Tillen and Spencer-Block and some Bruno-Kahn and so on. Okay, let me stop here. Thank you.